Thanks. We are also mostly working with sparse linear algebra, so perfect that I'm directly after my previous speaker. We are from KIT. The work that I'm presenting is kind of a joint effort from Professor Enrique, Goran, and our team at KIT. Goran is here kind of a bit more transparent because he's done with his PhD. Just as a side note. So I guess I don't really have to explain to you this graph. This is basically at some point over the development of processors, we got more and more cores, which means we need to adapt our algorithms to be in parallel. And the number of cores will, over time, even more explode. So parallelism is extremely important. This is the figure that I will mostly referring to. This shows the fraction between the peak performance given in megaflops and the peak bandwidth in megawords per second. And over time, this fraction increases year over year. So this tells us over time, the compute power grows much faster than memory bandwidth. And our conclusion from that is, since we are working with sparse linear algebra and mostly memory-bound kernels, is operations are basically free. So we can compute in double precision whatever we want, because our memory access is what counts, and we need to optimize the memory access. And that's why we kind of propose to decouple the storage from the arithmetic format. That means all computations that we also do in our Ginkgo software library are in double precision. And then depending on the algorithm, we can get away with lower precision numbers or lower precision memory. But we will still load this into registers, convert it to double, and then perform all the computations in double precision. Kind of now an evaluation of the V100. So this is the GPU or the accelerator that is in most supercomputers nowadays, especially in the first and second in the top 500, which is Summit and Sierra. It has 900 gigabytes per second memory bandwidth, around 8 teraflops double, 16 teraflops single, and 125 teraflops tensor performance, which is kind of half precision. I will from now on refer to this as the half precision format, even though it's kind of a matrix half precision. And if we now consider we read our values to just one computation, and that's basically it, you can see we get like 0.1 teraflops in double precision. So we are heavily memory bound. We're not even close to reaching the peak compute performance in double precision. Can also look at how many operations we need to do per value to reach the memory bound limit. So if we compute in double precision and read in double precision, we need 70 computations per value to be memory bound. If we instead load the value in single precision, do the computation in double precision, we only need 35, well, only. And the same kind of applies for half precision. So if we have our values stored in a reduced precision, we are a lot faster. And in this case, it doesn't really matter in what precision we compute, because even the 17, we will usually never reach the 17 computations, as these in sparse linear algebra. So we're not just looking at the IEEE formats, but we're also looking at the B-float, for example. So we use the floating point, cut it in half, so it is properly aligned with other values. We do the same for IEEE double precision. The advantage of that is we have the exact same number of exponent bits. So we have roughly the same value spectrum, just we have less significant bits. And In theory, you can also consider other lossy compressions like ZFP, but this is future work for us. So what we mainly use for now, reduced precision, is for approximate operators. So if you want to solve the sparse linear system AX equals B, you can precondition that with, well, the preconditioner being an approximate inverse. So this is the preconditioner, which is roughly the inverse of our system matrix A. But we sometimes need to even store this inverse in double precision because we have to ensure regularity. We cannot just reduce the precision. We have to ensure that the matrix stays regular. And as a preconditioner, we will from now on look into the Block-Jacobi preconditioner. So the Jacobi preconditioner just looks at the diagonal elements. Block-Jacobi has blocks on the diagonal, which we inverse. The advantage from that is we have more values and we can converge faster the larger the blocks are. So in theory, if we set one of those blocks to the size of the full matrix, we're done in one iteration. However, increasing the blocks, of course, also creates more overhead, and the whole operation gets more expensive and needs more memory. So the Block-Jacobi preconditioner, these are the rough steps. We have our matrix. We at first need to select the blocks. We do this with a super variable agglomeration. I will come to that later. We then extract these blocks, invert them. We do that on the GPU, for example. We load them into registers and then invert them in place. And after that, we store this back to main memory, so we can use that later on to apply the preconditioner. Because we generate it once, then we can apply it multiple times. We can store some, or depending on the matrix, most of these in lower precision, but like I mentioned, we need to ensure that these block matrices are regular. So these are some first evaluations that we did with 70 matrices, all from the sweet sparse matrix collection. Why is it? Sorry. And here you can see the condition numbers of these blocks. So these are always ranges of blocks. So up until 24 blocks. We have some outliers, but as you can see, the condition number varies strongly from matrix to matrix. We also combine now this preconditioner with the conjugate gradient solver to kind of have a real-life evaluation. Why? Jumping. So these are the number of iterations that the CG takes with the Block-Jacobi preconditioner. These are just here for reference. The more important part comes now. These are the kind of slowdowns or speedups of single precision Block-Jacobi compared to double precision. So these store the single precision Block-Jacobi, stores all values in single precision. The double precision stores everything in double precision. And as you can see, there are quite a lot of strong outliers with a kind of slowdown of up to 2.5. So we need 2.5 the amount of iterations with single precision compared to double precision. We did the exact same thing with half precision. Sorry. And as you can see, this is even worse because, probably a lot of those matrices are now irregular, and the preconditioner doesn't really provide any benefit. By the way, the scale is now changed. It's now logarithmic, so we get up to a kind of slowdown of 100. So our idea, I'd really like to know. Our idea is now to analyze these blocks look at the condition number that we get. So at first we invert the matrix, compute the condition number, and then decide for which precision we should go. So we have here the regular double precision, single precision, half precision, and those intermediate steps like the cut double precision. So we have 11 exponent bits, 20 significant bits, and also, well, we cut this even more, so we only have 4 significant bits. This is not really relevant, but we will see the evaluation later. And we also have the cut single precision, which is the B float. And our goal is to preserve 1 to 2 digits of accuracy, so 10 to the power of -9, 10 to the power of -2. This is kind of our goal for the preconditioner. So the advantages of this proposed preconditioner is regularity is preserved, because we basically try if it works with half precision. If it doesn't work, we test with single precision. If the matrix is still irregular, then we stick with double precision for this one block. We do these for all blocks simultaneously. We don't need a flexible Corolla solver because we do all the computations in double precision. We can also handle non-symmetric positive symmetric positive definite problems. Sorry, because our inversion contains a pivoting, and we can basically use this preconditioner for any iterative solver that can be preconditioned, which we also do in our Ginkgo framework. However, of course, it has some drawbacks, like it has the overhead of the precision detection. In the easiest case, this is just a computation of the condition number. In the worst case, we need to try things 2 or 3 times, so the generation is a bit more costly. We also need to store in which precision one block is stored, so we need an additional storage space. And the speedups is, of course, problem dependent, because in some, the preconditioner might not really help, in others it is extremely detrimental, so it varies strongly. So the matrices I showed previously with the condition number, we tried the exact same thing with, we evaluated how many we store in single precision, double precision, and so on. So on top, you can see all the different formats that we support. This is just for one matrix. We store half of it in double precision, the other half kind of in single. And this is for all matrices, so... Why? 1 second. Okay. So we have a strong mixture of all different formats. So for some, we need to store almost everything in double precision. For a lot of them, half precision is totally enough. And some need a kind of strong mixture out of like B float, single, and also a bit of double precision. This is now how many... Why is it doing that? This is the application runtime. Okay. This is how long it takes for the preconditioner application. So since we are on GPUs, we are kind of also bound by hardware. So one warp on NVIDIA is 32 threads. So that means we can handle up to a matrix, block matrix size of 32 by 32. This is the application of preconditioner with a block size of 16. So automatic is the second to the right. This is that detects the precision automatically. Auto short does not use single precision or half precision. This just truncates and see what fits. So this is a lot faster in generating. But like as you can see here in application, it doesn't really matter. And the others are just regular double precision. This has the least amount of gigaflops because it needs to load the most amount of memory. Then we have these two groups, which are all like 32-bit access. These three groups are these, which are each value is stored in like 16-bit, half precision truncated float or truncated double. And so you can see we're still heavily memory bound. But we are definitely faster with our adaptive version than double precision. And for this, we reach roughly equivalent time as single precision. And this is basically for all matrix sizes, for all block sizes that we support. And since it should be multiple, since it should be a power of 2, otherwise we kind of lose warp threads, 16 and 32 are the most optimal in terms of block size for these matrices. So now let's talk about speedups. We evaluate both the iteration, the number of iterations that we take with the adaptive version, and the time, so the runtime that we use. So this is preconditioner versus, well, adaptive preconditioner versus non-adaptive preconditioner, which uses only double. And as you can see, for the most part, the green is above 1, so we have a speedup of roughly 20%. The iteration count stays the same in most cases. We have some outliers, but overall, I think this is kind of a success. Oh yeah, and on the top, every one of those balls is if it does converge on its own with preconditioner and with adaptive preconditioner, and it converges with all of them. And these are outliers where the preconditioner itself provides more than 2 digits. So for example, if the preconditioner in double precision is a very accurate representation of the inverse, so it's very close to it, then it converges a lot faster. And since we only preserve like 1 to 2 digits, we converge slower than the original. So here the preconditioner is kind of too accurate for at least our runtime. Yeah, and that was basically it. Our work can be seen here. It's the Ginkgo framework. The precondition exists inside there. It is open source under BDS3 clause. We are also part of the multi-precision focus effort in the ECP math library ecosystem. You can also find our libraries in the XSDK project. And yeah, if you have any questions, feel free to ask.